Hey there, AP Chem Scholars. Excuse my scruffiness, but it's been a long day, and I want to make sure I get this video done for you. Who knows what this week is going to be like. So, today's video is going to be about section 3.7 and 3.8. 3.7 is a longer one, 3.8 really short. All right, so we're talking about solutions and mixtures. So when we talk about solutions, you know that we're talking about something that is homogeneous, where we have a solute being dissolved by a solvent. Okay. The process by which the intermolecular forces of the solvent are grabbing and pulling apart the solute is known as solvation. Okay, so it really is just a dissolving process. It's a fancy name. When water is a solvent, then solvation is sometimes referred to as hydration. Okay, that name unfortunately could mean a bunch of things, but that's where we are with it here. So we will talk mostly about water being a solvent, but not entirely. So hydration of sodium chloride. We've talked about ion dipole attractions already. So as we zoom in on this, we see the sodium chloride molecule being broken down. And down here we see the water molecules, those Mickey Mouses there. And the negative end, which is the oxygen end, is being attracted to the cation, and the negative end of the water is being attracted to cation, and the positive end, or the hydrogen end, is being attracted to the anions. And you see that it takes a bunch of waters to grab just one ion. That's where the idea of solubility is going to come into play. Okay? Different substances dissolve differently because it takes a bunch of water molecules just to grab one ion. Remember that ion-ion attractions are stronger than ion dipole. But if we get enough ion dipoles going on, then we can overcome that ion-ion attraction. All right? So it really depends on that strength issue. We know we've talked about precipitation in the past. Okay, crystallization is really the term for the reverse of solvation. Okay, so solvation is where the solute is being dissolved by the solvent. Okay, now crystallization would be where the solute is coming out and becoming solid again. Some terms that we need to be familiar with. Concentration. Okay, is a relative term. It talks about the amount of solute in a solvent. Specifically, we're going to talk about a couple ways of measuring concentration. But for now, solubility refers to the maximum amount of solute that can be dissolved in a given amount of solvent. Sometimes we use solubility in more generic terms. Is it soluble or is it not? But solubility really is a measurable quantity. And then we talk about a couple more generic terms: unsaturated, saturated, and supersaturated. Unsaturated means that a solution has less solute than its maximum, so less than its solubility. Saturated means it is at its solubility, and supersaturated means that it is above its solubility. Now you might have to be saying to yourself, how do you go above the maximum? But we've talked about this before. It's a temperature thing. The solubility of a substance is defined by temperature. At higher temperatures, solids will dissolve better. So if we raise the temperature, even though only, let's say at room temperature, only so many grams will dissolve, okay, by raising temperature, I can make it all dissolve, and then if I lower the temperature back down, it becomes supersaturated. However, when a solution is supersaturated, it is very easy for it to crystallize out, and you'll end up back at saturated. But it is possible to make a supersaturated solution. They're just a little delicate. A couple other terms. Miscible. Okay? Miscible has to do when we're talking about liquids dissolving in liquids. Okay? So alcohol and water, they are miscible, meaning that you could dissolve almost any proportion of water and alcohol together. Okay, that's what miscible means. Okay? This is an example of something that we put in our gas line because it's miscible with both gasoline and water. So if you have water in your gas line, this stuff kind of grabs onto it and then helps it burn off when the gasoline is burned. And of course, miscible means one thing, immiscible means the opposite. So these are liquids that do not mix in any proportion. So oil and water are the common examples, obviously, of immiscible liquids. Talked about the idea of solubility and temperature already. As we look at this graph, you see that most substances are increasing as they go to the right. Okay, there is two exceptions. This exception is really a bizarre one. This one will make sense in a moment. Okay, when we talk about solids, okay, first of all, again, we expect the solubility to increase, but also keep in mind when we talk about solubility, I forgot to mention that it's always assumed, these graphs, that it's in 100 grams or 100 milliliters of water. Okay. Now, compare that to gases. We expect the solubility of gas to decrease as the temperature increases. Why would that be? Well, a lot of it has to do with something called entropy that we haven't gotten into yet, but we could think of it just as an energy thing. Gases have more energy typically than liquids, so the idea of containing a gas in a liquid is already difficult enough. And if we increase the temperature, the gases are going to become even more active, and so it's just that much harder to contain them. Okay. It also has to do with the intermolecular forces of the liquid and the fact that as we heat it up, we're kind of weakening its intermolecular forces so it can't hold the gas as well. There's a number of factors. But if I go back to the previous graph, you could see that ammonia, which is a gas at room temperature, would decrease. That one does make sense. Concentration. There are several ways that you can measure concentration. Realistically, we focus mostly on molarity. In the past, I showed you molality. I'm not going to go back into it. It's there just as a reference point. Okay, but molarity, which is the number of moles of solute over the volume of solution in liters, okay, measured in molars, okay, that is very, very important for everything we do the rest of the year. Mole fraction will be mentioned a little bit. So mole fraction just means moles of one part over the total number of moles. And even though it's called a mole fraction, we express it as a decimal number, not as a fraction. It's really a stupid name, but there you go. Mass percent, we will see a little bit. Mass percent is a mass of one part, again, usually the solute over the total mass. We've seen this already when we talked about percent composition, or we said mass percent for that as well. So that's a very common thing. And then we have something else. There's parts per million, parts per billion. That's, again, reference. We're not going to see that. When you do water treatment things, you're allowed so much of certain chemicals in so many parts per million or so many parts per billion. So like, when they test water to see if there's lead in it, there is a set number of how many parts per billion, meaning out of billion grams of water, you're allowed just 1 gram of lead. Okay, or well, it's actually a little bit more than that, but still, that's the idea. Am I rambling today? Maybe. It's been a long day. I think I said that already. Anyway, so molarity, real quick, just a review. Okay, if I told you that a solution prepared from 117 grams of sodium chloride and 900 grams of water, the volume of the solution was 1 liter. Notice that I'm specifying the volume of solution, even though I have the mass of the water, because water is the solvent, but for molarity, it's moles per liter of solution. So we're just going to convert the grams to moles and go from there. So we take 117 grams divided by the molar mass, we get 2 moles. And so 2 moles divided by 1 liter would be 2 molars. Okay. All right. Need to mention colligative properties briefly. Now, again, those of you that had me, this was covered in the past. We're going to keep it very simple here because the AP has minimized this also now. So when we talk about colligative properties, we're talking about properties of solution that depend on the amount of solute particles, but not on the specific type of solute particles. So it doesn't matter whether it's a mole of ions or a mole of polar covalent molecules, as long as it's something that dissolves in the water, or whatever solvent we're talking about, than it is just how many of them there are. Okay, so it doesn't matter otherwise. Now, obviously, being an ionic compound versus covalent does make a difference because ionic compounds dissociate. So sodium chloride, when I put it in water, if I put 1 mole of sodium chloride in water, I'm really putting 2 moles of particles in the water because I'm going to get 1 mole of sodium ions, 1 mole of chloride ions, and so we get 2 moles out of it. So don't be misled by this, but the fact that I said 2 moles of sodium of ions were in the water, if I took 2 moles of sugar, I would get the exact same properties. So it's about the number of particles. Okay, again, that's the key idea. So if we're trying to boil water, okay, and we add something like sugar to the water, okay, not only was there hydrogen bonding going on with the water, holding it together, but now by putting in the sugar particles, we're going to have even more particles that are having their own intermolecular forces with the water, and that's going to prevent the water molecules from vaporizing as much. It's going to make it less volatile. Okay, so that means then, in effect, we are changing the water just by the presence of the sugar particles. Now remember, a solution is, when we make a solution, it's a physical change. It's not a chemical change. The sugar is still sugar, the water is still water, but together they have a little bit, some properties together, but it's still going to be sweet and it's still going to be watery. So the properties are mostly the same there. But now in terms of boiling or freezing or a couple other properties, that's where we're going to get into some differences. All right, I think I explained this idea already, but please always keep in mind the idea that like dissolves like. That is very, very important. The better, when we talk about making solutions, okay, polar solutes will dissolve better in polar solvents. Nonpolar solutes will dissolve better in nonpolar solvents. Okay, that's going to be true no matter what. So the type of solute does matter to a little bit. But again, it's really more important about how many particles there are. Run too far. Okay, I was there. So I think I pretty much explained that idea already. The number of sugar particles is more important than what type of particle. Now, I'm showing you this equation for boiling point elevation. Why I'm showing you the equation is not because we're going to do calculations with it. We are not. The AP does not require it. You just have to understand the theory behind it. So I'm showing it to just make sure you understand the theory. Boiling points change according to 3 things. Okay? K, which is a constant based on the solvent. Okay? For example, for water, Kb is 0.515 Celsius degree per mole. I, which is called the Van Hoff factor, I'll come back to in a second. M is the molality. Now again, you don't have to know molality, so why would we, again, we're not getting into the calculation, so it's okay. So what's the point there? All right, well, again, the Van Hoff factor is an important thing because conceptually it could come up on the AP. The colligative properties are all about the number of solute particles, but we have to take into account, like I mentioned with sodium chloride, the idea of dissociation. And that's where the Van Hoff factor comes in. Anything that would not dissociate would have a Van Hoff factor of 1. Okay? Anything that would dissociate, like sodium chloride or aluminum chloride or aluminum sulfate, is going to break up into multiple particles, and we need to talk about how many particles, and so the Van Hoff factor would be respectively 2, 4, or 5, depending on which of those compounds you're talking about. Sodium chloride has 2 ions, so the Van Hoff factor is 2. Aluminum chloride has 1 aluminum, 3 chloride, so it has 4 ions. The Van Hoff factor would be 4. Aluminum sulfate has 2 aluminums and 3 sulfates. That's 5, etc. Okay, so that's where the number of particles really comes into play. Same thing can be said for freezing point depression. Okay, we add the solute, we're going to make it harder for it to freeze, so we're going to lower the freezing point. I guess I should have emphasized that on the previous slide. We're going to raise the boiling point because it's more difficult to boil it, and we're going to lower the freezing point because it's more difficult to freeze it. Okay, and for water, the value is 1.86. You don't have to know that, but that's Kf. Again, different solvents would have a different value. but we're still talking about the Van Hoff factor. We're still talking about molality. So boiling point, freezing point really are very similar properties because we're looking at things a little similarly. We're just talking about extending the liquid phase upward or downward, depending on what we're talking about, boiling or freezing. There are two other ones I'm going to mention briefly. Vapor pressure depression. We talked about vapor pressure earlier in this unit. So again, when we put a solute into our solvent, it's going to make it more difficult for the solvent to vaporize. And so there's going to be less vapor pressure. No big surprise there. And biology talked about osmosis. Osmosis has to do with the net movement of the solvent through a semi-permeable membrane. Okay, so what's happening is it's trying to balance out concentrations based on osmotic pressure. So it's a pressure that actually causes things to move. Okay, and again, it's just an idea that it does depend. There's a Van Hoff factor again. Now this one actually does deal with molarity, but they don't ask you any questions about that. So I'm not going to go into the whole idea of the calculation. Just understand that it is a colligative property and you are good to go with that. Now, the title of the unit was Solutions and Mixtures, so we need to talk about the mixtures a little bit. Okay? When we use the term mixtures, we're usually talking about something that is heterogeneous. Yes, a solution is a homogeneous mixture, but if we just say mixture, we're usually implying it's heterogeneous. Okay, so first type are called colloids. Okay, a colloid, how do I explain this? Colloids are very much like solutions, except that they're not homogeneous, and the particles actually are reasonably larger, and that's what actually prevents it from being homogeneous. So you might look at that and say, well, how would I know the difference between a colloid and a solution? And there's a simple test for that, and this is an important thing to keep in mind. It's called the Tyndall effect. Do I not have, there is a Tyndall effect. I'll come back to the other one. When we shine a beam of light through a solution, it stays relatively together. When we shine a light through a colloid, it spreads out because it's scattering off of the larger particles. Okay, so we could easily tell the difference between a solution and a colloid just based on that. Okay, so keep that in mind. But when colloids particles become even bigger, they become more obvious. We call it a colloidal suspension. Okay, so again, heterogeneous, it's a colloid, but we call it a colloidal suspension because the particles are so obvious to the unaided eye. Okay, like a lava lamp. Okay, we can see the things mixing around, and we can see that it's not homogeneous. Okay, that's what makes it a suspension. There are many different types of colloids. You don't need to go into those. Used to be. Okay, but please, I just wanted to emphasize this because it's very important we understand that we always think about just putting a solid in a liquid, and that's not the case. Okay, there are many ways of combining these things. You notice that the only combination that is not there is gas and gas. Whenever two gases mix, it's always going to be considered a solution. Okay, but if we're mixing any other combination of phases, we could have a solution, we could have a colloid. Okay, so it is possible. Almost every combination could be a solution. Every other combination here could definitely be a colloid. And some other examples just for reference sake. Okay, so there are some things like fog, milk, mayonnaise, gelatin. Okay, those are all colloids. In the vein of colloids, we have to talk about hydrophobic and hydrophilic. Okay, hydrophobic, well, you know phobia means fear, right? So hydrophobic, we're saying these particles are afraid of water. They don't mix well with water. Okay, so that would be like the lava lamp that we saw. Okay, those particles are not really interacting with the water. They're just there, moving around on their own. They have really nothing to do with the water. On the other hand, we could have hydrophilic colloids. Okay, and these are things that the root there, phil, means love. So these are things that really interact well with water molecules. But generally speaking, the size of them makes them colloids because they're too big to be dispersed evenly by the water molecules. Then we could also talk about things that are amphipathic, which means, that amphi like amphibian, like, to an extent, like ambidextrous, okay? Something that is a little bit of both, okay? So something that is amphipathic is something like soap, okay? Soap is designed so that you can get stubborn stains out off your hand or whatever else that are non-polar things that won't stick to the water. You would stick your hand under and it doesn't seem to come off with just water because water is polar and the dirt is non-polar. But if we use soap, soap has a long molecule which makes it relatively non-polar, especially down this end. But down this end, we can see that it's definitely polar. We even have ions attached on it, so it's definitely polar. That's what makes it amphipathic. There's a general term for these surfactants, but things like detergents and whatnot are very commonly your amphipathic colloids. So now we need to talk about representations of solution. Like I said, this is the small part. So on the AP exam, they're really big now on particulate diagrams. That's why this gets its own section. Okay, you have to be able to look at these pictures and understand a couple different things about particulate diagrams. Okay, one, proportionality. Okay, as we look at these different pictures, and I'm going to hit this on the next slide anyway, but do some counting. In this one, which is 0.2 molar, we see 1, 2, 3, 4 potassiums, 1, 2, 3, 4 chlorides. All right, well, they should be in a 1-to-1 ratio. And in this one, which is 0.1 molar, I see 2 and 2. Well, that makes sense. If this is 0.2 molar, then 0.1 molar should be half as many particles, and it is. Well, let's compare it to another 0.1 molar solution. Let's talk about magnesium chloride. I see that I still have 2 of the magnesium, just like I had 2 potassium, but I have 4 chlorides. How does that make sense? Well, again, because it's MgCl2, we're going to get twice as many chlorides out of that, so it does make sense. All right, so here's another 0.1, and again, I see 2 particles, but wait, why isn't this dissociating? Because this is a weak acid. We haven't done really strong and weak acids yet this year, okay? But it doesn't dissociate. It does dissolve, so we do have 2 particles, just like we would have had, let's say, 2 potassium chlorides if they didn't dissociate. Since these don't dissociate, we just keep them as 2 particles. Okay, so you see that proportionality going on there. That's what I'm talking about here and here. Okay, so I think I've explained that already. I'm not going to belabor it. You could always pause it and go back to those slides. Intermolecular forces are also often represented on these diagrams, and we've seen the pictures of these already in places, and we talked about this idea already when we were talking about the hydration of sodium chloride, the fact that we have the sodium ion being, that's actually wrong sizes relative for sodium chloride, but whatever. The cation is being attracted to the negative end of the water molecules, and the anion is being attracted to the positive end of the molecules. So those come up as well a lot, okay? So that's really all you need to worry about particulate diagrams. Keeping in mind proportionality, keeping in mind intermolecular forces. Other than that, we'll build on it more as we go into other units, as we talk more about some of the solubility things and all that. All right? That's it for now. Have a good night.